Hello, everyone. My great pleasure to present a keynote entitled The Contribution of Photochromic Materials in the Development of Chemical AI. The outline. In the introduction, I will answer two fundamental questions. What is chemical AI and why am I developing chemical AI? Then I will focus on the contribution of photochromic materials, and I will show that they are valuable to implement three forms of causality related to biological intelligence, to develop quantum AI and neuromorphic engineering in wetware. Finally, I will conclude and present some perspectives. Let's get started. The development of ever faster, more pervasive transportation system and information and communication technologies has radically transformed humanity. Now humans are more linked to each other than ever before. Humanity as a whole gives rise to a vast and very dynamic network. And each member of this network, that means each of us, has to face not only their personal problems, but directly or indirectly, even challenges regarding the network as a whole. Such challenges are global for two reasons. They might regard almost everyone on Earth, and they are multi-sectorial because they encompass humanity from different perspectives. For instance, physical-chemical, biological, environmental, social, economic, and ethical perspectives. A list of global challenges is included in the 2030 Agenda, compiled by the members of the United Nations more than 10 years ago. This agenda contains 17 goals, assuring a sustainable development if pursued worldwide. And at the heart of this agenda, there are human beings and their societies, the world economy, the urban areas, the natural ecosystems, and the climate. These systems are instances of what we call nowadays as complex systems. Apparently, they are quite diverse. Traditionally, they are investigated by well-distinct disciplines. However, a systematic interdisciplinary investigation of this system began in 1980s has revealed that they share some features. And chemistry, being a central science, plays a relevant role in their analysis and management. The investigation of complex systems has revealed that there are at least 4 obstacles outlining in understanding and predicting the behavior of complex systems, outlining the so-called epistemological complexity. A contribution to the epistemological complexity derives from computational complexity. Many computational problems regarding complex systems are solvable but intractable. It means we cannot determine their exact solutions in a reasonable time, even if we use the fastest supercomputers in the world. Another contribution to the epistemological complexity derives from the recognition of variable patterns that are emergent properties of complex systems. We still lack the formulation of a universally valid and effective algorithm for the recognition of every type of variable pattern. These two contributions to the epistemological complexity reveal that we need to improve our computational capabilities. A promising research line is natural computing, where scientists coming from different disciplines draw inspiration from natural phenomena to formulate new algorithms, propose new materials and architectures to compute, and new methods and models to understand and manage complex systems, based on the rationale that any distinguishable physical-chemical state of matter and energy can be used to encode information. And every natural transformation of these states is a kind of computation. Within natural computing, we distinguish two programs. In the first, scientists exploit the physical-chemical laws to make computation. In the second, scientists mimic the information gathering and utilizing systems that belong to living beings. The research line of chemical artificial intelligence sprouts from the two programs of natural computing and is trying to answer the following heuristic question. Which biological intelligent competencies can be mimicked through inanimate chemical systems in wetware in a liquid solutions, which is the characteristic phase of life? Traditionally, artificial intelligence is developed through two strategies. One relies on software running on current electronic computers or special purpose hardware. And such software either reproduces the human thinking process when it is a flow of rigorous logical operations, or it mimics some structural and functional features of neural networks to learn how to perform tasks from data, or it mimics some other natural rational phenomena, for instance, biological evolutions or coherent quantum phenomena. Another more recent strategy to develop AI is through reverse engineering neurons and their networks in hardware in the solid phase to devise neuroprosthesis and to design brain-like computing machines, revolutionizing the von Neumann architecture of current electronic computers because processor and memory are in the same space and they develop in 3D rather than just in 2 dimensions. Another recent strategy to develop AI is chemical artificial intelligence. It relies on molecules and macromolecules that operate as if they were hardware. And all the physical-chemical processes, such as chemical reactions, chemical waves, diffusion, migration, advection, and convection, that can occur in the liquid phase when we are out of equilibrium, that operate as if they were software. In other words, the hardware and software of conventional AI are merged in the wetware of reactive solutions maintained in out-of-equilibrium conditions. Here I report a provisional map of chemical AI where we distinguish 3 main pathways. The first relies on the imitation of the rigorous logical thinking, implementing forward causality, and the implementation of other forms of causality. A second pathway is neuromorphic engineering wetware, and a third, more recent pathway is quantum AI, drawing inspiration from the quantum phenomena that support some biological intelligent competencies. Here, I report a knowledge map of chemical AI that is a 3-dimensional graph projected on a plane. Along the x-axis, we have the chi-domains that are molecular and supramolecular chemistry, system chemistry, and multiscale chemistry. With multiscale chemistry, I refer to all those chemical systems that manifest self-organization at different spatial scales, and multi-level causality, when appropriate macroscopic thermodynamic forces are applied. Multiscale chemistry is required to mimic some structural and functional performances of multicellular biological organisms, exhibiting multiscale competencies. That means the capability of processing different types of information at different spatial scales. In the knowledge map of chemical AI, along the y-axis, we have the chi paradigms that are all the biosensor, the brains, forms of brains, and biofactors we find in living matter. The third dimension reports the biological intelligent competencies, whose complexity is proportional to the saturation of the green color. They range from sensing to perceiving, from computing to planning, from working to acting. Some of these competencies have already been implemented. They are indicated in black. Some others have not been implemented yet. They are indicated in white. Probably will require a further development of system chemistry and multiscale chemistry to make these competencies be within reach. Or probably some of these competencies cannot be implemented through inanimate chemical systems at all. This uncertainty is not surprising. Suffice to think that the two sets of competencies are separated by a still unexplained concept, that of consciousness. Now we know what chemical AI is. So the question is, why am I developing chemical AI? Well, chemical AI can be valuable for facing epistemological complexity because it will be helpful. It's helpful to propose new materials and architectures to compute, to formulate new algorithms, and propose new models for understanding complex systems. Another ambitious goal of chemical AI is the development of chemical robotics. A chemical robot is envisioned as a confined, complex molecular assembly that reacts autonomously to its environment because it has sensors collecting data about the external environment, the internal state of the robot. It has artificial neural networks processing the sensory data making decisions and triggering the actions of the effector models that can affect the surrounding environment and the internal state of the robot. The intelligent activities of a chemical robot should be sustained by an appropriate metabolic model. Chemical robots should be easily miniaturized in order to be implanted in living beings and interplay with cells and organelles to perform biomedical actions. For this purpose, the lymphocytes are the best prototypes for chemical robots. But we might think of deploying chemical robots in the environment to fight pollutions or face problems related to energy and food supplies. For these purposes, the microorganisms that populate our soil are the best prototypes. So it's evident that chemical robotics opens a new avenue in the field of robotics. It's somehow related to soft robots, but chemical robots should be easily miniaturized to colonize the microscopic world. And finally, the development of chemical AI might have a curious side effect. The development of chemical AI will assist human efforts to unveil the mysterious event of the appearance of life on Earth. That staggering event has been described as a phase transition from a completely abiotic world to a world where the first complex, confined chemical systems capable of exploiting matter and energy to handle information and pursue goals somehow pop up. And now, as I promised at the beginning, I'm focusing on the contribution of photochromic materials to the development of chemical AI. Any photochromic compound is a molecule that, after absorption of photons having appropriate frequency, changes its structure, its color, and other physical-chemical variables. And the transformations are reversible. For instance, this pyroxazine, upon UV radiation, gives rise to a merosonine that also absorbs in the visible region, and this structural change is thermally reversible. Other photochromic compounds are only photoreversible. Others are both thermally and photoreversible. Finally, there are indirect photochromic compounds that are color in their most stable structure. After absorption of visible light, they give rise to a metastable uncolor structure, and after discontinued irradiation, we have a recovery of the original color structure. Photochromic compounds can be exploited to implement the three forms of causality shown by living matter, more specifically, forward causality, final causality, and circular causality. Let's start from the forward causality or direct causality that is essential for reproducing the rigorous deductive reasoning of humans. In this regard, any photochromic compound is a molecular switch or molecular transistor. More specifically, a direct photochromic compound with UV photons as input and the color as output can give rise to the yes logic functions, whereas an indirect photochromic compound with visible photons as inputs and the color as output gives rise to the not logic function. Many photochromic compounds are sensitive to various physicochemical variables, and they become multi-switchable chromogenic compounds. For instance, this pyroxazine, upon UV radiation, gives rise to a band at 611 nanometers because a merosonine is produced and the solution becomes blue. If this pyroxazine is UV radiated in the presence of at least an equimolar amount of protons, it gives rise to a band centered at 485 nanometers, and the solution becomes orange. If the same pyroxazine, the same band and the same color can be achieved when this pyroxazine is UV radiated in the presence of at least an equimolar amount of aluminum ions. Whereas if this pyroxazine is UV radiated in the presence of at least an equimolar amount of copper ions, it gives rise to a band centered at 423 nanometers, and the solution becomes yellow. See, it's evident that using three chemical inputs, a network of 5 molecular states is built, and starting from this pyroxazine, it's possible to navigate the entire network and return to this pyroxazine because the transformations are all reversible. So using UV photons as power supply, protons, aluminum, and copper ions as chemical inputs, and the absorbance values at the maxima of the bands produced in the visible region, after discretizing the input and output variables, this pyroxazine can be exploited to build 3 independent circuits involving 20 fundamental Boolean logic gates, AND, OR, and NOT. And these circuits work in parallel. So it's evident that the computational power of this multi-switchable chromogenic compound is truly remarkable. But photochromic compounds can be also exploited to implement final causality. Here I report a scheme showing the usual mechanism of unimolecular photochromism. We start from the original uncolor structure, and after absorption of a photon, UV photon, we jump to the excited state. Then the molecule traces a path that is almost barrierless. It crosses a conical intersection and it reaches the minimum or the ground state of the color structure. And this pathway is traced because the molecule can minimize its free energy through the fastest route. This behavior is a physicochemical version of teleonomy that represents the intrinsic goal-directedness of living beings. Moreover, any photochromic compound under stationary radiation gives rise to a photostationary state that is stable. It responds to small and temporary perturbation by recovering the original photostationary state. That means in the photochromic phase space, the stationary state is an attractor, is surrounded by a basing of attraction, and after any small temporary perturbation, there are negative feedback actions restoring the original photostationary state. So this behavior is a mimicry of homeostasis that represents the power of living beings to maintain the values of certain physicochemical variables stationary despite the fluctuating properties of the surrounding environment. Moreover, photochromic compounds can be exploited to implement circular causality. The significant structural change that accompanies any photochromic transformation from S to M can affect the surrounding environment, but also influence it by the surrounding microenvironment. And I show you an example. Let's focus on the 11-Schiss retina. When it absorbs visible photons having appropriate frequency and is embedded in the apoproteins, in the opsins, in the proteins we have on the retina, on the photoreceptor, on the cones and rods of on our retina, then it photoisomerizes to all trans retinal, and this structural change determines a structural modification of the apoprotein, triggering a cascade of biochemical events, leading to a final neural signal of the sensory cell. If the same photoisomerization of 11-Schiss retinal is carried out in a pure solvent in the absence of the apoprotein, then we don't achieve just the all-trans retinal, but a mixture of photoisomers. So it's evident that photochromic compounds affect the microenvironment, but are also affected, influenced by the properties of the surrounding environment. So it's evident that photochromic compounds are adaptable and are relevant ingredients of molecular cybernetics. We can add more. Any photochromic compound embodies a molecular Markov blanket. Likewise, any living being that preserves its identity based on its internal states through sensors and actuators, which constantly interplay with the external environment. In the case of a photochromic compound, for instance, this pyroxazine, the sensor are the original structure. The actuator is the merosign, and the internal states are the Frank Condon and all the other intermediate excited states that make decisions. Any photochromic compound performs this sensing, decision-making, actuation loop in any environment, and they can affect the environment, but also influence it by the environment. Now I want to tell you that photochromic compounds are also valuable to develop quantum AI, a cutting-edge research merging quantum information science and artificial intelligence. As far as human vision is concerned, the first step, that is the photoisomerization of 11-Schiss retinal, occurs as a quantum coherent phenomenon after absorption of ultra-fast laser pulses, because the 11-Gs retinals cross the reactive path in the form of wave packets. But the quantum features of human vision are not restricted to the first step, but they extend to color discriminations. In the center of the retina, we have three types of cones, the so-called red, green, and blue cones. Each of them has its own photoreceptor protein. So we have three photoreceptor proteins that share the chromophore, the 11-Gs retinal. However, since the three proteins have different amino acid composition of the pocket embedding the retina, the three proteins have distinct absorption spectra in the visible region. These three bands are associated with distinct transition moment integrals. It means distinct vibronic wave functions. But these three bands work as three fuzzy sets granulating the visible region. A fuzzy set is different from a classical Boolean set because an item can belong to a fuzzy set with a certain degree, which can be any real number included between 0 and 1. So lights having peculiar spectral composition excite the three photoreceptor proteins at different degrees. That means these lights having distinct spectral composition belong to the three molecular fuzzy sets at different degrees. And the granulation of the visible region is a form of quantum parallelism that enables humans to distinguish around 200 hues. Drawing inspiration from the mechanism of human color discrimination, we devised biologically inspired photochromic fuzzy logic system to extend human vision in the UV. We started from a collection of 5 thermally reversible photochromic compounds. Each of them has its own absorption profile in the UV, and each of them produces a peculiar absorption band in the visible region. The hue color generated by one photochromic compound is always the same, whatever is the excitatory wavelength in the UV. But if we prepare a mixture of these compounds, then we can discriminate the three UV regions by giving rise to colors having peculiar hues. And for the design of this mixture, we should mimic the human color vision. So we granulate the three UV regions and the visible region. For instance, this quaternary mixture involving compounds 1, 2, 4, and 5, whose absorption spectra shown here in the UV. Each compound has at least one peculiar absorption band for each of the three UV regions. Becomes green, gray, and orange when irradiated by frequencies belonging to the UVA, UVB, and UVC. So drawing inspiration from human color vision, we could design biologically inspired photochromic fuzzy logic system that extend human vision in the UV. And finally, photochromic compounds can also be exploited to develop neuromorphic engineering in wet work, where we start from the idea that the computational power of any neuron relies on its dynamical properties. In the nervous systems, we might encounter neurons in excitable regime, either tonic or phasic, but also neurons in oscillatory regime and in chaotic regime. Photochromic compounds are valuable for implementing some dynamical surrogates of some neurons. For instance, any thermally reversible photochromic compound under stationary and uniform irradiation can reproduce the dynamics of neurons in phasic excitable regime that respond in analog manner to external stimuli. On the other hand, when a solution of a thermally reversible photochromic compound is irradiated only at the bottom and the solution is maintained in uncapped cuvette, due to the partial evaporation of the solvent on top, we have a cooling effect at the top. We generate a vertical thermal gradient, triggering the convective motions of the solvent. We obtain the so-called hydrodynamic photochemical oscillator, where the merosanine spread throughout the solutions through color hydrodynamic waves with a velocity of 2 millimeters per second. And if we record how the absorbance in the visible changes over time, then we detect large amplitude oscillations that are actually aperiodic. More specifically, they are chaotic. So the hydrodynamic photochemical oscillator becomes a neural surrogate, or a surrogate of neurons in chaotic regime. Finally, we found out that by simulations that two couples of properly chosen photochromic compounds can give rise to the oscillatory regime. And these two couples involve two thermally reversible photochromic compounds that interfere in absorbing the exciting light, and they react in two distinct time scales, one faster than the other. Then we can achieve the oscillatory regime. After implementing neural surrogates, we put them in communication through optical signals. And for the optical communications, we devised three basic communication architectures as prototypes. The so-called alpha architecture, where the transmitter and the receiver are in the same cuvette and in the same phase, possibly with one component segregated within micelles or nanocapsules. The so-called beta architecture, where the transmitter and the receiver are in the same cuvette and in two immiscible phases, and the so-called gamma architecture, where the transmitter and the receiver are in two distinct cuvettes. To devise networks, we upgraded and hybridized these three fundamental communication architectures. Using optical signals and our neural surrogates, we could reproduce the synchronizations in phase, out of phase, anti-phase, and some of the phase-locking synchronization conditions. In conclusion, photochromic materials are versatile and find multifaceted application on chemical AI. This same versatility explains the widespread occurrence of photochromic compounds throughout the kingdoms of life. Photochromic compounds can be found in animals, plants, fungi, microorganisms that live in direct or indirect contact with the solar light. In terms of perspectives, chemical AI is helpful in addressing epistemological complexity because it promotes the design of new materials and architectures for computing, the formulation of new algorithms, and the development of new models for understanding complex systems. Chemical AI and chemical robotics will help humans explore and colonize the microscopic world, and decolonization of the microscopic world will provide tools to effectively combat poverty, clean up the environment, overcome diseases, and extend human longevity. Finally, trying to obtain intelligent chemical system from scratch can help understand intelligence and life. To conclude, I acknowledge my current collaborators, my past and present students, the European Union and my university for the financial support, and all of you for your attention. You can follow me on the social media because I like disseminating the subject of complexity and chemical AI. Thank you for your attention.